In this video, we're going to be doing a rotational FRQ practice for AP Physics 1 Unit 5, rotations. A block of unknown mass is attached to a long, lightweight string that is wrapped several times around a pulley mounted on a horizontal axis through its center, as shown. The pulley is a uniform solid disk of mass m and radius r. The rotational inertia of the pulley is described by the equation I is equal to 1/2 mr squared. The pulley can rotate about its center with negligible friction. The string does not slip when on the pulley as the block falls. When the block is released from rest and as the block travels toward the ground, the magnitude of the tension exerted on the block by the string is Ft. Determine an expression for the magnitude of the angular acceleration AD, alpha d, of the disk as the block travels downward. Express your answer in terms of m, r, ft, and physical constants as appropriate. So, what we have is, we can write this down. Mass is, we have m, we have r, we have moment of inertia, and we have no slipping. And the pulley is going to rotate around its center with no friction. Frictionless. We want alpha d, angular acceleration of the disk. So we're going to identify first the torque on the disk. So the only force that's producing torque about the center is going to be the tension. Now, tension, we know we can get that from using torque. So we know that torque is equal to RF sine of theta. So let's look at our disk again. When we have a disk, it's like this, and the tension is pulling on it like this. The center of mass is here, and our lever arm is the distance from the force on the object to the center of mass. So that is going to be our R here, our lever arm. So that is going to be perpendicular. So this is our force of tension, Ft, and it's the tension force is pulling the block up, or that's just, yeah. So that's our magnitude. Here we know it's going to be tangential. So Ft is going to be tangential, or theta is 90 degrees. So that means our R is going to equal to the radius of the circle. So that means that our torque is going to equal to Ft times R, because sine of 90 degrees on the unit circle, that's right there, or sine of 90 degrees is going to be a height of 1. So this is 1. That means this is going to be FTR as your torque. Now after this, we want to apply the rotational Newton's second law. Rotational Newton's second law states that the torque is equal to the moment of inertia times the angular acceleration. Now we can substitute in what we just found as our torque here into our expression. So our torque is equal to FTR, and our I is equal to our value up here, 1/2 mr squared. So 1/2 mr squared, and our alpha is going to be alpha of the disk. So solving for alpha of the disk, this is going to equal to FTR divided by 1/2 mr squared. And we can cancel out 1r. So we're left with Ft over 1/2 mr. And we want to move that 2 to the top, so we can switch this to 2 Ft over mr. This is going to be our solution for part A. Now we're going to analyze scenario 1 and scenario 2. So each scenario shows a different pulley. In scenario 1, the pulley is the same solid disk referenced in part A. In scenario 2, the pulley is a hoop that has the same mass m and a radius r as the disk. Each pulley has a lightweight string wrapped around it several turns and is mounted on a horizontal axle as shown. Each pulley is free to rotate about its center with negligible friction. In both scenarios, the pulleys begin at rest. Then both strings are pulled with the same constant force Fa for the same time interval delta t, causing the pulleys to rotate without the string slipping. After time interval delta t, the change in angular momentum of the disk is equal to the change in the angular momentum of the hoop, but the change in the rotational kinetic energy for the disk is greater than that of the hoop. Consider scenarios 1 and 2 at the end of the time interval delta t. In a clear, coherent paragraph length response that may also contain equations and drawings, explain why the change in angular momentum of both pulleys is the same. So angular momentum change of both pulleys is the same, but the change in rotational kinetic energy is greater for the disk. So in order to understand why the delta L is going to be different, the delta L is going to be the same, but you're going to have a different delta K, we can look at the angular impulse momentum theorem. So this states that delta L is equal to the torque times the change in the time interval, or just the time interval. So we know that torque in both scenarios is equal to the torque times the force applied times the R. So we know that in both pulleys, we have the same Fa, same R, and the same delta T. Therefore, we know that delta L is equal to FAR delta T. Now, this is going to be the same for both the hoop and the disk. So that means delta L of the disk is equal to delta L of the hoop. Now, why is the rotational kinetic energy different? This is because rotational energy is equal to 1/2 I times omega squared. But in angular momentum, L is equal to I times omega. If you solve for omega, omega is equal to L over I. And if you sub that into energy, your omega here, you're going to have that this expression is equal to 1/2 I times L over I, and you square that. So this is going to equal to 1/2 L squared over I. So that means that energy is inversely proportional to the moment of inertia. Now, after this, we can compare the moment of inertias. So we know that inertia of a solid disk is equal to 1/2 mr squared. And we know that the moment of inertia of a hoop is equal to mr squared. So that means that our hoop is going to be greater than the inertia of the disk because the inertia of the disk is being halved. So now we can also compare the energies. So comparing the energies, since we know that K is equal to L squared over 2I, that means that if you have a smaller I, because I is in the denominator, if I is bigger, you're dividing a number by a larger number. And if you do that, then it causes the overall number, the fraction, to be smaller. That means that the K of the disk is going to be greater than the K of the hoop because the inertia of the hoop is greater than the inertia of the disk. So you can see that they're inversely proportional in this relationship because having a larger inertia of the hoop creates the K of the disk to be larger in comparison because it's going to make that fraction larger if you have a larger inertia in the bottom. So we can write this in a paragraph. So in both scenarios, the same constant force is applied at the same radius for the same time interval. So the torque and angular momentum or angular impulse are identical. Therefore, both pulleys experience the same change in angular momentum. Since delta L is equal to torque times delta T. However, as we stated, the disk has a smaller moment of inertia than the hoop. Because kinetic energy rotational is K is equal to L squared over 2 times I for the same angular momentum, the object with a larger or with a smaller moment of inertia has a greater rotational kinetic energy, and that's because I is in the denominator. Therefore, the change in kinetic energy rotational is greater for the disk than the hoop. So that means, so essentially the same delta L, because same torque times time. And then here, or this is actually for part B, the same delta L because you have the same torque times time. And also the disk has a smaller I. So that means that for the same L that you have a smaller I, that's going to result in a larger K.